All right, so welcome back. We are Game 2005, that's Game Physics, in the fall 2020 semester at George Brown, and it's week 2 of our broadcast. So we are sitting at week 2. Today is September 17th, and we're talking about motion in one direction. I'm working on your assignment. This is net new, so I'm working on balancing it with Alex. I'm kind of vetting it with them to make sure it's pretty good. I will release it today, and I'll give you the details. If I can, I'll do a little demo video on what I'm looking for you guys to create for your assignment. And again, it'll be due 2 short weeks from now. It'll be something that is a programming assignment, and there may be some parts of it where you need to submit an assignment document, like a report. Chances are, though, what I'm going to include is a YouTube or some kind of video report that I want you to do for you and for your partner. Again, I'm looking at trying to make it so that it is a pair programming exercise, so 1 or 2 people. Actually, it's going to be 2 people. I don't want it to be less than 2 as a pair programming exercise for you guys. So that's coming up. So look for that. I will announce when it's released later on today, because that's when it's supposed to be done. And it'll be due 2 weeks from now, let's say on the Friday or Saturday. So there's nothing for you to panic about or whatever. It's going to be something to do. You're going to be using the SDL framework, our assignment framework, to work out your assignment. Okay, so that is assignment 1. That's going to happen. So today we're going to be talking about motion in one directions. Let's talk about that. Okay, so we're going to start talking about something called kinematics. And guys, I'm going to occasionally look over on the right for for your feedback. What I have is a participants panel. If you need to get my attention, please don't put it in the chat necessarily. I will look there as well. Yeah, by do something like that, Kira. Perfect. By putting up your hand, or and then that'll kind of signal me that I need to do something. My participants panel is actually closer to my eyes on the right hand side of my right monitor than the chat. I try and push that a little bit more away, so that way I can really notice when you need something. Okay, so please use the participants panel to get my attention when I'm going through this chat. Okay, so kinematics. So it describes motion while ignoring the external agents that might have caused or modified the motion. And for now, we'll consider motion only in one dimension along a straight line. And motion for us represents a continual change in an object's position. So that's the vector that we're looking at, the position vector. There are several types of motion: translational motion, rotational motion, and vibrational motion. What we really care about for this course and for some of the stuff that you're doing over the course of this semester for your projects is usually translational and rotational. Vibrational, typically we don't look at. Okay. When we start thinking about objects, when we start thinking about physics, one of the easiest things for us to do and to simplify our lives a little bit, and especially when we think about how to model these things, is we use the particle model. All right, I'm just going to shut down all my sounds. I'm sorry, I get binged and bonged like crazy, and unfortunately it's not something that I want to interrupt you guys with. So it sometimes makes a little bit more noise than I'm liking. I'm also going to pull up something called NVIDIA RTX Voice, which I'm using to reduce some of the noise. And you should see as soon as it comes on with my blue Snowball microphone, it'll cut down things like pops and that kind of thing. All right, so that's what's happening. All right, so again, continue. So we use a particle model to simplify our lives. And what I mean by that is, even if the object is very large, like let's say, for example, the object is a spaceship, we think about it as a particle when it comes to moving it around the screen a lot. Unless we're actually creating a rigid body, and in the beginning we wouldn't. We're going to start thinking about a very simple physics engine example, where every object we consider is a particle. Okay? So it means like we only care of one point, one single point on that object, or the center of mass is what we're looking at. Okay? The object's position is at a location with respect to a chosen reference point, and typically it's the origin. Okay, so we have, let's say, for example, 0, 0 on the number line. We're looking at motion in one direction anyway right now. So we can consider things like the number line as the origin. And when we look at object A, it's 30 units right to the right or positively away from the number line. Okay, and again, this might be a review from some of you, so that's why we're going over this. We can also look at object B. It's something like 50 some odd units if we look at the middle of the object, 50 something units away from the origin to the right, right? And we're only interested in the car's translational motion, so we model this whole thing as a particle. We don't really care about rotational motion in this case at all, and we don't really care about vibrational motion. So we can look at the center of mass, and we think about it as the center of its coordinate system. Actually, we do that a lot for game objects too. If I have a game object, usually it's centered, right? So we think about the pivot of the game object in the center, and then we look at the coordinate system of our game, and wherever the center of that object is, that is the quote-unquote location or position of that object from a transform perspective. Okay? Okay, let's continue. So we also have something we can map position in this position time graph. Okay, so this is an example. So here on the bottom, we can look at this as in time in seconds. So 10, 20, 30, 40, 50 seconds. You can also look at this as 10, 20, 30, 40, 50 frames instead of seconds in your game. And here is the position from the origin for this particular object. So you can see that it starts at position A around 30 units away from the origin, okay, in meters. Let's say this is in meters, so 30 meters away from the origin. In 10 seconds, it moves to about 50 meters away from the origin, and then it drops back to something like, in 10 more seconds, it drops back, goes back the other way, and goes to about something like 35 meters away from the origin. And then in the next 10 seconds, it's at the origin again. Then it's behind the origin, and then it's way behind the origin. Behind meaning like to the left. Okay? So you can see that from a position time graph, what this does is it maps our motion for us. And actually, this is something that's useful for us. A motion graph is something that we can use to describe motion of an object like an enemy. I wanted to use a motion graph to describe its motion, back and forth, side to side, and so on. And you can use these motion graphs for everything like easing in and easing out as well. That's also very useful. A lot of times we use a data table to describe the actual positions in X and Y coordinates. Remember that in this case, X axis is used for time, so this could be seconds or frames, and the Y axis is used as position, and this could be meters or pixels. It really depends on how you look at this, right? And this is meters or pixels outside of the origin. Now, obviously, if we're in negative space, most games, if we're looking at a game, if I'm on negative something, that means I'm either off screen or to the left or to the top left or bottom left, depending on your coordinate space. But typically to the left or bottom of origin, or typically to the left and top if we're gonna do a 2D coordinate plane. So again, when we represent the car itself, we have a few things that we can use. We use a picture, some kind of image. One thing that I'm going to be asking you guys to do this semester is I want you to, if you're solving a problem a lot of times, we may need to draw a picture. I want to draw an image, kind of like what we did last week when we talked about the distance away from the tree. We're kind of figuring out the formula for the distance away from the tree kind of idea. How do we figure that out? So first we draw a picture, first thing we do. And then we do some math, right, as an example. That's kind of what we do in sequence in order for us to understand the picture that we've drawn. So we start labeling the picture to make it so that it matches our model, whatever the model is that we're trying to use. There's other alternative representations we can use, but that's kind of where we start. Okay, here's another term, displacement. Okay, so again, we're moving into more terminology for physics, and I'm kind of ramping you in slowly. Okay, so displacement is defined as the change in position during some time interval. Okay. And displacement is different than distance. So think about what this thing is. So it's represented as delta x. That means the change in x. Delta normally means change in physics. Delta x, in this case, is the change in the x-axis only. And we have something called x final minus x initial. So whatever the final x position is, you subtract the initial position, and then you get the change in position. Usually we use it in the standard units are measured in meters. That's what they are. Okay? And delta x can be positive or negative. And one thing to note is that displacement itself is different than distance. Displacement and distance are a lot of times thought to be the same thing, but actually it's not true. Let's give an example here. Here we have an example of a basketball court. Assume a player moves from one end of the basketball court to the other and back. Distance is twice the length of the court, but displacement is 0. Why? Delta x is equal to x final, so the final position, minus the original position. Since the final position and the original position are the same, therefore the total displacement of a person moving all the way this way, and I'll make this a different color. So all the way that way, let's say across the court, let's use a color like, I don't know, we can make it red. We'll make it red. So let's say maybe red's not good. Maybe we'll make it green, like a light green color or something. We'll make it bigger and thicker so we can see it better. There we go. So we move this way across the court and we move back, right? As an example, make moving back a different color. We'll make it blue. So kind of maybe a light blue color, and we'll make that a little bit thicker too so we can see it. All right, so we move across the court and back across the court. You can see that it's twice the length of the court, so the total distance is twice the court length, but the total displacement is 0. So please keep that in mind, the difference between distance and displacement. Okay? You'll be asked questions like that in your test. Vectors. Okay, you guys should know about vectors by now. I mean, we've been talking about vectors over the course of several semesters now. You learned about them pretty much in semester 1, and now we're talking about them again, and they're in semester 3. We can use positive and negative sides to indicate vector directions, right? And usually, remember what a vector is. It's both distance, right, and direction, right? So magnitude and direction is what we're looking at from the origin. Typically, is what when we think about a vector. We're also going to be thinking about the averages of things. So here's something. This is one of your first formulas for kinematics, the average velocity formula. Okay, let's think about this average velocity formula. What it means? It's the displacement on the x-axis over the change in time. So the change in x over the change in time. And of course, you can break these down into x final minus x initial. So the position on the x-axis, the final position, minus the initial position over the change in time, right? And that's your average velocity, which is different than an average speed, right? Because velocity we use for displacement. Speed we use for distance, which is totally different. Okay, so again, the dimensions are in time, or in length and in time, and the units are in meters per second. Length over time, meters per second. Okay, it's also the slope of the line in the position time graph, right? So again, if I was to look at the position time graph, it's the slope of that line. Okay, or a tangent, if you will, to the curve, which we're going to be talking about again. So speed is a scalar quantity, whereas velocity is a vector quantity. All right. So speed is a scalar because it is the same units as velocity, but we don't care about displacement. We care about distance. So the total distance over time. Okay. And that's the speed of an object. Sometimes we interchange. We make the mistake of interchanging distance or speed and velocity, right? Why? Because typically we don't go backwards. And what I mean by that is we don't describe a motion graph for a cannon. A cannon pretty much goes in one direction, away from the cannon. The cannonball leaves the cannon and keeps going in the same direction, typically, unless it somehow bounces off and comes back, right? But typically it doesn't bounce. It probably just breaks through whatever it's hitting, right? Same thing with a bullet. A bullet usually penetrates the thing that it's trying to hit, right? So it doesn't come back. And so that we describe things, even though that we're describing a displacement, it's really very close to a direction and a distance, as opposed to a direction and a displacement. So again, average speed and average velocity. The average speed is not the magnitude of the average velocity. For example, a runner, if they end at their starting point, their displacement is 0, but their velocity is also 0, but the speed is not 0 because of the distance they traveled. All right. Again, I'm just hammering the point here with these slides. The limit of the average velocity is the time interval becomes really, really short, or as the time interval approaches 0. That's the limit. And a lot of times what we want to say is we want to have the instantaneous velocity at every point in time. Guys, instantaneous velocity, we skipped calculus, right, is, if you think about it, the derivative of the position graph. All right, so when I look at the position, the derivative of the position is velocity, right, at instantaneous velocity at every point in time. That's what it is, okay? So in other words, if we look at tangents, these are tangents to the curve, right? And these are secant lines, right? That kind of go this way, that cut the curve, right? So if we notice, the light blue lines show that the delta time gets smaller, right? As we approach the green line, which is the instantaneous velocity at tangent to the curve. This is the curve, and the instantaneous velocity is tangent to that, okay? The instantaneous velocity, remember, velocity is a vector, so you have both direction and magnitude. If I have a direction and magnitude, I have an angle that's outside of the horizontal. So the horizontal typically just, kind of, we think about it as the x-axis in this case. The x-axis is the horizontal, right? The vertical is the y-axis when we talk about the vertical. So when we want to have the angle between the horizontal and this vector, which is the velocity vector in this case, right? That angle can be figured out with the stuff we talked about last week, trig, typically, and Pythagorean theorem a lot of times, because we're normally in a situation where we're using a right angle triangle. And that's why right angle triangles are so important to game development. A note about slopes. Slopes have units unless both axes have the same units, and then the unit is removed typically, all right, or we cancel it out. More or less, slopes, if it's rise over run, and the rise represents the distance and the run represents the time, or we can say if the vertical represents the distance and the horizontal represents the time, then it's time over distance over time, right? And again, if you think about that relationship, it is y over x. And it normally is. If you notice, every single time we talk about a relationship between the axes, it's always y over x, not normally x over y, okay, typically. I just wanted to point that out. So the instantaneous velocity can look like a limit. And for those people who forgot what limits look like, it's read like this. The velocity across the x-axis, this is how you read it, is equal to the limit as the change in time approaches 0, right? So that means the instantaneous time, the time at that particular moment, right, on the curve, right? When I'm looking at that moment in time, right? Of the change in x over the change in time, so delta x over delta t, which can really be written like this, dx over dt, which is actually if you think about what the velocity means, it's the derivative of the position graph. That's what we talked about before, right? So if you understand calculus, it means we can derive the velocity from the position. We have position, we look at a position graph, I can look at the instantaneous velocity at that point in time, and I have the velocity, okay? So again, instantaneous speed then is the magnitude of the instantaneous velocity, all right? The instantaneous speed has no direction associated with it because we don't care about direction when it comes to speed. It's just distance over time. So the total magnitude of the distance. Okay, again, vocabulary note. Velocity and speed will indicate instantaneous values. Average will be used when the average velocity or the average speed is indicated. Okay. What we do a lot of times when we look at physics problems is we use analysis models. Okay. We want to try and place a model on top of the real world, right? Which means I have an idea of some equations. I understand kinematic equations. How do I apply different kinds of things that we've observed in physics to different situations and make some calculations, make some predictions based on what we've noticed in nature? We use an analytical model or analysis model. And what it is a description of the behavior of some physical entity or the interaction between the entity and the environment. Okay, that's what the analysis model lets us do. We try to identify fundamental details of the problem. So try and derive the components of the problem or break it out into little smaller problems when we look at, when we try to apply physics to it. And it's based on 4 simplification models. One is the particle model. Another one is the system model. A third one is the rigid object model. And the fourth one is the wave model. Notice that particle and wave are separate, but whenever we try to model something like light, we can model it as both a particle and a wave. Okay, so, and again, you might have learned that in Physics 101 in high school, that they talk about the wave particle theory of light and that kind of thing. Good old calculus, exactly. So the way we approach a problem is we identify the analysis model that is appropriate for the problem, and then the model tells us which equation to use to understand the problem, okay, to really break down the problem and make some predictions. Okay, so let's think about a model, a particle under constant velocity. Okay, so this is a good example of something that happens in our games too, something that moves in a constant rate of speed. Can anyone think about an object, and let's be creative here, an object that moves at the same rate of speed all the time on the game? You can use the chat for this. Fireballs. Thank you, Kira. It could be, yeah. What other things? Can we think about any other option for an object that moves at the same rate of speed? Sometimes fireballs can speed up and slow down. Enemy bullets, yes. We're talking about projectiles. They can move at the same rate of speed. Most projectiles. Here's something. What about our background? Is that something that can move at the same rate of speed if we're scrolling? If we have a scrolling background? The answer is yes, probably, right? As well. So the same rate of speed means, notice that the velocity vector, normally it's applied to bullets though, like you guys are saying. So notice that if you see the particle here, there is a vector, and the vector is the exact same length every single time. Same length, right? The vector has a direction to the right, and it's equal, right? For each snapshot. These are all snapshots of the particle moving to the right. Okay, so constant velocity indicates that the instantaneous velocity at any instant during a time interval is the same as the average velocity. So instantaneous velocity, same as the average velocity. In other words, we can say that the velocity on the x-axis is equal to the average velocity of the x-axis. In that case, when we break down the math, we can say that velocity on the x-axis, which is really a delta x over delta t, when you break it down like this, we can say that we can move things around, and we can say that it's equal to the final position minus the initial position over time. And if you just rejig everything across the equals sign, so we just use algebra to rearrange our stuff, we can see that it breaks down like this. The final position is equal to the initial position plus the velocity times the difference in time. Guys, this is the beginning of all of our equations we'll be using in physics from now until the end of the semester, right? When it comes to kinematics and motion. Why? Think about what this is saying. That means I start off with the initial position. What's my initial position? 0. What's my velocity across the x-axis? Let's say 10. Okay, cool. I start off with position 0. 10 is my velocity, 10 units per frame, 10 pixels per frame, 10 meters per second, right? Then I multiply it by the number of seconds I'm modeling. So example, delta time, the change in time, how many seconds have passed. So let's say for a second, I want to look at 3 seconds. I want to look at from time 0 to time 3. 3 seconds. So I take my speed or my velocity, which is 10, multiply it by the number of seconds, 3, and I get 30. 30 units, whether it's meters, pixels, whatever. 30 units is the answer. That's the final position. The final position is 30 units away from the origin, if I was going to use those numbers. Again, common practice is to let the time initial be 0, like it says here, and the equation becomes x final is equal to x initial plus vxt. All right? For constant velocity x. Okay? If it's not constant velocity, you cannot use this equation. There you go. That's a beautiful equation there, Kira. All right, cool. So if we think about this, here's the graph of a particle under constant velocity. So here's the time in units. This is the graph. And here's the displacement, if you will, in units, meters, as an example. This is time in seconds or frames. It doesn't really matter, right? And then you can see that the velocity is constant. It's a linear slope because it's constant velocity. It's not something that's going up and down. If it was going up and down, the motion graph would appear different, right? All right, a particle under constant speed. Okay, that's different than under constant velocity. Remember that we don't care about the displacement for speed. We only care about the distance that the particle has traveled. So example, if I was going to model this out for a constant speed, right, then we care about the path that the particle is taking, right? Whereas for a constant velocity, we don't care about the path. We care about the distance. If I was going to draw an arrow between the origin and the ending point, that's what I care about for the displacement, for velocity, right? So if I look at, let's just make that a different color, and we'll format the shape into something like a red color so we can see it, and we'll make it bigger. So again, if you think about this, we care about from a displacement from here to here. We don't care about how it goes up and goes down. This is a waste of information for us when it comes to velocity. All we care about is from here to the end. But a constant speed does care about those things. It cares about the path that the particle takes. The total distance is much longer than the displacement in this case. Okay. So again, what we do is we look at, for speed, notice that speed is not a vector, but actually a scalar quantity. We look at the total distance traveled along the path over the change in time. Let's also think about average acceleration. The average acceleration is, I want to take the change in velocity, that's what we define it as, a change in rate of velocity, all right? So acceleration is the rate of change or change of rate of change of velocity, which means the change, the delta velocity on the x-axis over the delta time. That gives us the average acceleration at every instantaneous point in time. So that's the instantaneous or the average velocity over that time period. So what I would do is take the final velocity minus the initial velocity over the final time number, whatever that is, over the minus the initial time. The dimensions are length over time squared, because you can see that we're going to say meters per second squared is what the units are going to be. So length over time squared. In one dimension, positive and negative can be used to indicate direction. So I want to go to the right, I want to go to the left, I want to go up, I want to go down. That's what positive and negative average acceleration gives us. The instantaneous acceleration is very similar to the average acceleration. We take the delta v as an example, delta velocity over delta time, and we get these deltas. We get the delta velocity over the delta time on the x-axis, which is equal to delta x squared over delta time squared. That's what it looks like. and this is for instantaneous acceleration. Notice the little graph here on the bottom, and I'm going to zoom in here so you guys can see it even better. You can see that the average velocity grows every single time slice. So we start off with a small vector, and the vector becomes bigger and bigger and bigger and bigger. That means that the velocity is moving up. The rate of change of velocity is increasing. Therefore, there is an acceleration. If the rate of change of velocity was not increasing, if it was staying the exact same, if the velocity was the same magnitude every single frame, therefore there would be no acceleration. There'd be zero acceleration. Acceleration means there must be a change in velocity. In this case, it's a fixed acceleration. All right, so the acceleration is not changing. That's not what we're talking about. It's a fixed acceleration, a constant acceleration. By the way, a lot of the things we do in physics is under a constant acceleration, something that's accelerating across a constant value. When we have a delta for the acceleration, then it becomes more complex to do our calculations. Okay? A lot of times because we're losing mass. And I want to talk about that. So rocket science is a good example. I'm going to start talking about rocket science now. The reason why rocket science is difficult is because if I'm accelerating a rocket, the way the acceleration is going, we're going to be talking about this more with Newtonian physics, is I'm propelling the rocket forward by expelling propellant from the back of it. And for each action, and we're going to find out, is we have an equal and opposite reaction. So if I expel propellant in a specific area or a specific amount in a direction, I'm usually going to propel myself in the opposite direction. So I spit stuff out from the bottom of the rocket, and then I go up, as an example. But the problem with rocket science is when we want to figure out the fuel required, well, guess what? We're going to have a lighter and lighter mass, and which we're going to be talking about soon over the next couple weeks, which means the amount of propellant that's required is going to change as the mass decreases over time. This is a difficult calculation. And this is where our acceleration will continue to go up and up and up based on the same amount of propellant coming out of the back of a rocket. All right, if I keep spitting out the same amount of energy at the back of a rocket, I'm going to continue to accelerate faster and faster. I'm going to have a delta alpha, which is going to be very difficult to calculate. So also that gravity decreases as you get further away from the surface of the Earth slightly, right? So what ends up happening is you have a very challenging equation. Okay, here we're not talking about that. Here's a very simple equation where acceleration is constant. And most of the stuff we're going to be doing in this semester, as well as most of the things you do in game development, is with a constant acceleration, right? Almost never do we have a changing acceleration, typically, all right? And why? And even if you were, you would just calculate it. You would use funny numbers to fudge the result, okay? Because it's too complex to calculate. So the slope of the velocity time graph is the acceleration. So if I take the derivative of acceleration, in this case, I get, the derivative of velocity is acceleration. So again, I'm just going to zoom in on this graph now so you can see what I'm talking about. So if this describes velocity, right? And remember, velocity is a rate, a change in displacement over time. Okay, so you can see that I'm here, and then here I'm kind of changing my velocity. This is the red line, is the velocity line, and the blue line is the rate of change of velocity from one point to the next, one time frame to the next, right? Time final minus time initial is the delta time, right? And then velocity final minus velocity initial, that's the delta v, right? We can get a derivative of that to get the constant acceleration from A to B. Notice it's just a straight line. That's why we call it constant acceleration. If acceleration was a curve too, the acceleration curve, it would be more difficult to calculate. All right. So therefore, we can use these three graphs, and this, by the way, sums up everything we would do for when we start off in calculus. In calculus, we start off with a position, right? Or displacement, if you will. And then that would be this one. The top graph would be the position graph, okay? And it's all relational. So from the position graph, using the same time interval, we can derive the velocity or motion graph. And from the motion graph, we can derive the acceleration. Notice it tells us a story, right? So here, if I was going to ask you, what story does this tell you? If you're only given the velocity, right, you could actually see that it does tell you something. It means that I'm moving away from the origin. That's what this means. So my velocity increases. That means my displacement increases. Here, I stopped for a time, where the time between positions, I'm not changing my displacement anymore. Although it seems that my position did change physically from here to here. My time changed, and so did my position on the x-axis. But my velocity stayed constant, right? Position changed, velocity stayed constant. I have zero acceleration. That's what this means. Look, and down here, you can see that I have zero acceleration during this time interval from time A to time B. I do move, but I'm moving at a constant rate of speed. Constant rate of speed means no acceleration. That's why you see this flat. Then, right, from time B to time C, I am changing position, but my velocity is dropping. Therefore, I have a negative acceleration for a bit. We don't like to say negative acceleration, but we do have a deceleration, if you will. Slowing down is what's happening, right? Because I'm moving I have less displacement over time than I would between A and B. Okay? And you can see I continuously accelerate until I reach zero acceleration, so zero velocity. When I reach zero velocity, notice that my displacement starts going from where I am here. I'm losing displacement. I'm losing position. I'm going back to the origin. That's what this graph means. I'm going backwards here at this point, right? Because the distance from the origin is decreasing, right? That's what this means. And you can see that I now have a negative velocity. That's what's happening here, right? And then I go from here to here, and I go back towards the origin. And if you notice, now I have a constant acceleration going from some kind of negative speed to a positive speed. All right, that's what's happening. I'm moving towards the origin. And so I'm going in a positive direction. I'm increasing my speed. That's what this acceleration means, right? And then I'm going to stay at the same rate of speed for the rest. And so my acceleration again drops to zero. And that's what these graphs mean. So there's a relationship between position, velocity, and acceleration. And you should know this for the things that we're doing this semester. Okay. When an object's velocity and acceleration are in the same direction, the object is speeding up. When the object's velocity and acceleration are in the opposite directions, the object is slowing down, right? And that makes sense, right? Because we're going to be talking about that. We're also going to be talking about force, not now, but there's a footnote here. This is really a footnote slide, which talks about the acceleration of an object is related to the total force exerted on the object, where force is measured in newtons. We're going to talk about newtons in a couple weeks. The force is proportional to the acceleration. So the more acceleration I have, the more force I need to use. And that's part of Newton's second law, which is force is equal to mass times acceleration. If you think about that, just that equation alone, force is equal to mass times acceleration. If I want to move to the speed of light, this is why people say that the speed limit of the universe is light speed, because as I move closer to light speed, my mass increases to infinity as per Einsteinian laws, right? E is equal to mc squared, where energy is equal to mass times the speed of light squared, right? So if that's true, the amount of energy then that I need to expend to increase my or to accelerate my mass to light would be infinite, and therefore I can never get there. And that's why when people say there's no way we can ever meet light speed or even 10% of light speed, is because the closer we move towards light, our mass and becomes dilated, or so they say, increases, mass actually increases. Somehow you start becoming more massive as a particle, if you will, and therefore the amount of energy increases to infinity. So we would have an infinite amount of energy. All the energy in the universe couldn't push you to the speed of light by Einsteinian laws. Is that accurate? We've seen our observations are actually matching up with that thing. But remember, we're also looking at things from our frame of reference, our limited frame of reference as human beings. Maybe there is a way of flashing outside of our frame of reference into some kind of subspace where time between meters is measured in, instead of measured in seconds, it's measured much longer or shorter. So why did I tell you that? Because you're going to see relationships between force and acceleration. Negative acceleration does not necessarily mean the object is slowing down. It just might mean that it's going in a different direction. And the word deceleration has a connotation of slowing down. Physicists don't really like that too much. Here's some motion diagrams, which you're also going to see in this course, right? So you're going to see this first one. So here's a velocity, and you can look at this one, the first one, A. We can see a car that's moving in the same direction, right? Moving in to the right at the same rate of speed. We can say that in this case, because you can see the car is equally spaced across each frame, each instance that we're capturing, we can say that the car has zero acceleration. All right, because we're actually capturing each instance of time. That's what we're doing over and over again, right? Here, the car has constant acceleration. Notice that there's an acceleration vector down here, right? The acceleration vector is the same size every single time, and it's going in the same direction as the velocity vector. But notice that the velocity vector, the arrow in the velocity vector, is growing, which is what should happen if we have an acceleration. The car here is getting faster and faster, and so for each time slice, it's farther and farther apart from the previous time slice. So I look at the first frame and then the second frame, they're pretty close together, right? But then it gets farther and farther and spaces apart. This is a good example, a good picture of acceleration in the same direction as velocity. When we have acceleration in the opposite direction of velocity, though, you tend to have things slow down, right? We see that there's a large amount of velocity here. The velocity vector is quite high. And you can see that there's quite a bit of space between the two cars, but my acceleration vector is in the opposite direction. So what I'm actually doing is I'm subtracting my acceleration vector from my velocity vector every frame. That's what's happening until I have zero velocity. And when I reach to zero velocity, chances are I'm going to have zero acceleration. Chances are, unless I go back before the origin. Okay. Then I might have negative acceleration. So this is a motion diagram that can be formed by imagining a stroboscope or some kind of, in our case, frames. We're taking frame snapshots. Okay. Hopefully you guys are on board with this. Are you guys all with me, by the way? And I'm trying to go slow because this concept stuff is what gives us an idea of how to make smooth motion. Guys, when I say, are you with me, I want a check mark on the participants panel, or an X if you don't understand. So please, let's see those check marks, please. Not yups on the chat. I can't look at the chat when there's so many of you and only one of me. There's 72 participants. I want to see check marks. It's easier for me. All right. So most of you are on board. Most of you are understanding. This is good. Thank you guys for participating. All right. Let's move on. Constant velocity. So again, when we talk about constant velocity, just to go over this again, the images are equally spaced. Acceleration and velocity. The images and the of the cars are farther and farther apart because, and both going in the same direction. When both arrows are going in the same direction, the car is speeding up. We can say that the car is accelerating. When the arrows are going different directions, we can say that the car is decelerating. Okay? They're going in different directions. So, in all previous cases, the acceleration was constant, as shown by this violet arrow. And the diagrams represent motion of a particle under constant acceleration. particle under constant acceleration is another useful analysis model. Because if we were going to try and figure things out about particles under changing acceleration, that would be a different model altogether. Our models are mostly going to be around constant acceleration. Let's think about kinematic equation now. So we talked about kinematics, motion, and now we're going to be using some equations to describe the motion. And you're going to see that the equations I'm going to represent today in motion in one direction can be extended to 3 dimensions. First, we're going to talk about 2 dimensions next week. But today, let's start off with these simple fundamental equations that we can extend. So kinematic equations may be used to solve any problem in one-dimensional motion. And again, 2 of the equations to solve one problem. Sometimes we need to do that. We need to use 2 equations and 2 unknowns, or a system of linear equations we can use. And for people who remember linear algebra, we can use a system of linear equations to solve our problems. Sometimes we need to do that. Oh, this is weird. Wow, what happened there? That is wacky. That's a slide translation issue. Yay. Okay, so let's get back to this. So for constant A, we can say that we missed our equation. That was our equation there. So what would you think our equation for a constant A? And let me see. Hopefully we didn't lose that equation. Okay, yeah, we did. But that's okay. I'll go back and I'll plug this. Let's look at the next one. But let's look at this one first. So for consistent A, the first equation is I have the displacement. That's really weird. Whatever happened there. That's terrible. Let me see if I can pull that out. Hold on, guys, because that messes me up. I get mad when I see that kind of stuff happen. Bear with me. I usually make PDFs, and usually I have that information at least in a PDF that I can capture. That's a terrible thing. Terrible, I said. Yes, I do have it. Okay, so that's good. I'll just capture it and I'll plop it in. What a terrible thing that happens to me. There we go. That's what I meant. For a constant acceleration, let's get back to this. Velocity final is equal to velocity initial plus the acceleration on the x-axis times time. Okay, so this is the first equation. And this is kind of what we talked about before, right? The final velocity, the initial velocity, so if you think about this, the initial velocity, if it was 0, we start off at 0. And if the time was 0, right? Well, we have no motion, right? When the time is 1, we take the acceleration. If the acceleration is 0, so there's no acceleration, all we care about is the final velocity is equal to the initial velocity, right? Pretty straight. However, if we are accelerating and if we want to figure out the final velocity, because that's what we're finding out with this equation, and if the acceleration, let's say, is 5 units for every second, and if I look at it 10 seconds away, I'm going to add the acceleration vector to the velocity vector multiplied by how many time slices I'm looking at. So a good example of that is if I have 5 seconds or 5 frames, let's look at time as 5 frames, and if my acceleration across the x-axis is 5 units per frame, 5 times 5 is 25 units that I'm adding into my initial velocity. And if my initial velocity was, let's say, 10 units, I take 25, add 10 to it, and I have 35 units is my final velocity, right? So it would accelerate. I can say that I'm accelerating. This assumes that the initial time is 0 and the final time is time t. Okay, one thing this equation does not give us is it doesn't give us any information about the displacement. Not really. This just tells us that there is displacement. We don't know how much displacement because we don't know the initial position. But one thing to note is this. If I have the final velocity, let's say, for example, the final velocity ends up being 35. And because we know that the final velocity is a derivative of the position, right? then we can say that the original position is 35x on the x-axis. As an example, 35 units across the x-axis if we plug in values of x. Okay, let's think about the second kinematic equation. The second kinematic equation talks about the average velocity across the x-axis. So the average velocity of the x-axis, you take the initial velocity plus the final velocity and you divide it by 2. Pretty simple. Average velocity. Anything, if you have two values that are relatable and you divide them by 2, if I have 10 values and divide it by 10, I get the average or mean. Constant acceleration. All right, so if for constant acceleration, I want to find the final position. That's what this tells us, okay? The final position is equal to the initial position plus the initial velocity, the average initial velocity, right, times time, which you can rearrange to look like this. So there's two equations here, if you think about it. There's the first part of the equation over here. Let me just annotate that. So this is the first part of the equation. And we can take this equation and we can make this equation out of it, right? What we're actually doing is we're just taking velocity average and we're saying that the velocity average, like we had before, right? Sorry, I just want to stop annotating. The velocity average we had before is, if I go back up a slide, is this. Right? So we're taking this and substituting into this part right here, right? And that's why we're getting this. We're just rearranging the equation. So we can say that final position is equal to initial position plus 1/2 of the initial velocity plus the final velocity times time. Okay? Again, this is very close to the equation that we can use for a lot of different situations. In other words, final position is P naught. Sometimes we say naught as in the initial or 0. You know, P naught plus V naught T. Okay, is what we say. Here's the most famous one, and you can apply this to 2 dimensions as well. You know, you just sub out the x final and just you put in there position final, where position has 2 components, x and y. Okay, here we only care about one component on the x-axis, so we say the final position is equal to the initial position plus v naught t, initial time times the initial velocity times time, plus 1/2 of axt squared, which gives us a beautiful parabola. If you're going to look at the motion time graph, kind of something that looks like this, right? Why? Because if I plug in values of acceleration, let's suppose we plug in some numbers, and off the top of our head, if I say something like, if the initial position is 0, so I'm at the origin, and my initial velocity is 10 meters per second, right? And my initial time is 0, but I'm going to travel for 2 seconds. So I would take my initial velocity, 10, times 2, that's 20 seconds. So far, or 20 meters per second. 20, right? And then I add 1/2 of my acceleration times time squared. If I have a constant velocity, so no acceleration, then acceleration becomes 0, and now I've traveled v, which is 10 times 2, which is 20 meters. That's my final position, 20 meters away from the origin. However, if I have an acceleration, let's say, for example, I have an acceleration of 5 meters per second. I increase every second 5 meters my velocity. So then I would add in 5 times time squared, time being 2 seconds, like we said. 2 times 2 is 4. 5 times 4 is 20. 20 divided by 2 is 10. We add 10 meters to the velocity. So that would be 20 plus 10 is 30. So my final position is 30 meters away from the origin. All I'm doing is substituting the information that we know. And that's the first thing we do. We take the information we have and we sub in. Okay, when we try and figure out these formula. Here's the next one, kinematic equation number 5. So we can think that our squared velocity, final is equal to squared velocity initial, right, plus 2 times acceleration on the x-axis times the displacement in position, x final minus x initial. This gives us the velocity in terms of acceleration and displacement, and notice that there's no time in here at all. Sometimes we don't have a time, but we do have the final velocity and we do have the initial velocity. So in other words, if I start off at 0 and I say, by the time the bullet reached the position, this X number of meters away from the origin, right, it accelerated to 30 meters per second, okay? From, let's say, from 10 meters per second, the final, let's say, would be 30. The initial is 10, right, across the x-axis. If we have the acceleration, right, then we can figure out the position. If we don't have the acceleration, but we have the positions, we can figure out the acceleration by rearranging this equation. Okay? Here, we don't need time. Here, we need time. And sometimes we don't have time when we're given a problem. So that's why we have all these different kinematic equations. By the way, one equation can be derived from the others. It's just a matter of doing the proof, which it's out of scope for this course. So here's when the acceleration is 0. When the acceleration is 0, funny things happen. We know that when acceleration is 0, then the velocity is constant. Velocity final is equal to velocity initial. We know that. And we also know that when acceleration is 0, that the final position is equal to the initial position plus vxt. And this is actually an equation we're going to see in next week's lecture as well, because we can use it for things like bullets on the x-axis. Bullets on the x-axis don't slow down or speed up. The y-axis is where we slow down and speed up, right? We have acceleration due to gravity, and it's pulling our bullet down, and it's accelerating it faster and faster. So we wouldn't be able to use this equation on the y-axis. But on the x-axis, if we had no such thing as gravity, we would have this equation. The bullet would keep going and going and going until it hits something, right? The same rate of speed. The reason why the total velocity of a bullet changes is because of gravity. All right. So here's your kinematic equations in a nutshell, in a summary. Okay. So again, v final is equal to v initial plus axt, which is velocity as a function of time. X final is equal to x initial plus 1/2 of vx initial plus vx final, right? X means the position on the x-axis, by the way. And that is a position as a function of velocity and time. And this one, x final is equal to x initial plus vxit plus 1/2 at squared, axt squared. This is a position as a function of time. But we don't have time. Notice time for these three. If we aren't given time, we can use the bottom one. So here's a graphical look at motion. A lot of times what we want to look at, and one of the things that I may ask you to do on your assignment is take a look at the tangent to a slope, or the tangent to a particular curve, right? So here's a tangent to the curve. And whenever we look at something that's tangent to the curve, it's like if I could look at the center point, or if you can picture this as slices of a circle, right? And if we can draw a perpendicular line from the instantaneous slope, as an example, then we will get what we call tangent, or right angles. It's at right angles to the curve. That's what we want to say. Right angles to the curve. This way. Right angles to the curve. It's almost like what we call the normal. The normal to the curve, right? Towards the center. That's what it is. And that's what the slope is. And if we think about that, we can get a instantaneous acceleration or instantaneous velocity, depending on what we're looking at from the slope. So that's a graphical look at motion displacement over time. So here is the x in terms of distance away from the origin, and here is time. Distance over time, or displacement over time, is velocity. Here's a graphical look at motion, a velocity time curve. here the velocity is linear, therefore the acceleration is 0. Slope is the acceleration. The velocity is increasing. This is velocity on the x-axis. Here's time. If velocity increases, then slope is the acceleration. If there was 0 slope, so if the acceleration was going from left to right, then you would have 0 acceleration. And here's a graphical look at motion acceleration time curve. If the acceleration is straight like this, if the slope is 0, that means the acceleration is not changing. It's actually constant. Okay, so constant acceleration. And this is a further breakdown of what we saw earlier when we had those 3 graphs. Are you with me? I know it's kind of going through the same material a little bit slower, but we're kind of halfway through, a little bit more than halfway through, and now we're going to be talking about another philosopher. Thank you for me. So we talked about Pythagoras last week, and this time we're going to be talking about this guy here, Galileo Galilei, who is was a famous Italian physicist between 1564 and 1642. He formulated the laws of motion for objects in free fall. And he also supported, which is kind of weird and got him into a lot of trouble, the heliocentric model of the universe, which means he thought that the sun was the center of everything. And of course, the church didn't like that, and they killed him, I think, at the end. Because they believed that the God is the center of the universe. And the earth is the center of the universe. They supported the geocentric model of the universe, where he said, no, it's the sun. And he was wrong, actually. The sun is not the center of the universe. So for freely falling objects, he observed a few patterns. One of the things that he observed is he thought about what happens when I drop an object, from my hand, an object at rest, as an example, or an object from a shelf. What happens when an object falls from a shelf? That's one behavior. The other one is, what if I take an object and throw it downward? What happens to that object, right? And also, what happens when I take that same object and throw it upwards? Okay, what happens to that object? So he made these 3 simple observations. Okay, let's describe these 3 observations in more detail. So the acceleration of a free-falling object. Again, we're only talking about motion in one direction here. We don't care about lateral movement here. No x movement. Now it's only on the y-axis we're looking at. Before, we were only looking at the x-axis. Now, we're only looking at the y-axis. We found that he measured that gravity, after several experiments, equated to 9.8 meters per second squared, approximately, for every object, no matter the mass. Okay, that's what he found. So if you think about what that means, it means that it doesn't matter what your mass is. Now, this is assuming that the object is not shaped in a way to attract resistance from wind. So, for example, I'm not shaping a parachute or something like that. If the object is in the shape of a flat plane, even if it's a larger, more massive object, it's going to experience wind resistance. So here, what we're saying is, all things being equal, with no wind resistance. For example, it's a rock, right, or something that's got less wind resistance than something that's planar, right? Then gravity is pretty much, it accelerates roughly 9.8 meters per second. Now, one thing that Kiera said is correct, which is gravity decreases with increased altitude. But it's so small, it's hard to measure at increased altitudes until it's farther away. Okay, the farther and farther an object comes away from the Earth, the less and less pull the Earth has on that object based on its distance. And that makes sense. For example, the Earth is not going to pull on far away objects outside of the solar system. If gravity was constant all the time on every object in the universe, then the whole universe eventually would implode, and all the objects would just rush together, as an example, right? But that's not the case, right? So gravity doesn't work like that. One thing to note before we move on from this, which is interesting to me and should be interesting to you as computer scientists, if you will, or just scientists in general, little amateur scientists that we're making you right now this semester, is that gravity, we still don't know a lot about gravity. After all these years, scientifically, we still don't understand what makes gravity exactly work. Not exactly. There is no graviton particle that we can measure, right? It's not like I can look at a particle and say that, hey, these particles act on a particular object, and this is why we have gravity. I can't reverse the polarity of a graviton particle to have anti-gravity, although we would love to have that kind of capability in some kind of science fiction reality, right? But that's not the case. We have no idea really how gravity acts on us, other than we know this. Two objects with mass pull on each other. Even us, we have a small amount of gravity, very, very microgravity, that pulls on other objects. Very, very, very small. So small that it's difficult for us to measure. But because we're made of mass, we have atoms, and we're made of molecules, so too do we have gravity. Every object in the universe has some kind of influence in the space-time continuum in this way. And I'm not going to go too much into, these philosophical things. But every one of us has gravity, but only a small amount. So we don't really understand how that works. But we just know it does work. One thing that we do when we talk about free fall, we neglect or we ignore air resistance. We don't care about that because it makes it easier for us. Once we start talking about air resistance, we add a negative acceleration, or we countermand the acceleration due to gravity. Normally what we say is acceleration on the y-axis is also equal to negative gravity, and negative g, where g is acceleration due to gravity, or a negative 9.8 meters per second. This is for motion in one direction. That's what we do, right? So just to know that is the case, okay? If I was going to talk about gravity in another frame of reference, we may not use negative gravity. It might be positive. In this case, because we're talking about free fall, we're talking about negative. Why? Because it's going in the negative direction, which is down for us. The positive direction for us, from a Cartesian plane perspective, is up, right? And that's not what's happening here with gravity. So when we have an object in free fall, we drop an object, and we start an object at velocity 0, right? So the velocity is 0. My acceleration is negative g, or negative 9.8 meters per second squared, right? We use the kinematic equations, as an example, and generally we use y instead of x to record the acceleration due to gravity. So again, we can use the acceleration where we had that final velocity is equal to the initial velocity plus 1/2 of at squared. We would just sub in velocity on the y-axis. The initial position would be the position on the y-axis in this case, because all we care about is the y-axis when we're falling. If an object is thrown downward, then the initial velocity, this one, cannot be 0. We start off with a velocity as it's thrown down. For example, if I throw an object, a rock, downwards from a height at 10 meters per second, I'm throwing it with energy. There's energy being transmitted from my hand to the rock that's propelling this thing down at a particular velocity. So if I'm throwing an object down, the velocity cannot be 0. These are just properties of what we're talking about here. If we're throwing an object up, the initial velocity also cannot be 0, but we see a special phenomenon where there's going to be a time when, if I throw an object in the air, it's going to reach a point where the velocity becomes 0. Why is that? Because every instant that the object is being propelled in the air, gravity is acting upon it and slowing it down, and slowing it down, and slowing it down, until it reaches its peak, the apex, if you will. And then it starts to fall. It starts at velocity 0, and it accelerates from this point, the peak or the apex, slowly, 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 until it reaches back to where I threw it. Here's a point of fact. Whatever the velocity is upward, when it comes to this point, it's going to be the exact same velocity in the downward direction. Right? So in other words, if I throw something up at 10 meters per second, if I'm able to do that, When it comes up, loops back and comes down, and it comes back to the level of my hand, it's going to come back at me at 10 meters per second. Guys, this is a really great example of why you don't fire a gun straight up in the air. All right? You fire a gun straight up in the air, it's going to come right back at you in your head, right? At the same level of velocity, right? That's just standard the way things work. That's why if you notice, if they do a 21 gun salute as an example, you see the riflemen, they always point away from the people's, they don't point their guns straight up. They point away. Unless, of course, they're crazy people. When there are crazy people in this world. I mean that as in like silly. Okay, so let's think about this. So again, the thrown upward, if I throw it upward, the motion is symmetrical. So the time it takes to go up is the same time it takes to come down. The velocity that I throw up is the negative velocity when it comes down to the point where I threw it. So the motion may not be symmetrical, right? If, as an example, I'm at a higher place. If I start off on a hill and I throw an object up into the air, it's going to come down to where I threw it and keep going. And that's where I have asymmetrical motion. Okay, here's the example. So I'm here on top of a building. And at time equals to 0, let's zoom in here. At time equals to 0, at the top of this building, I throw this object up. So it launches from my hand, goes up until it reaches the apex, right? Where the acceleration due to gravity and the velocity, the initial velocity, cancel out after several seconds, 2 seconds, right? And then the velocity becomes 0 up here on the y-axis. It starts to fall. And when it comes to this point, notice what we see. The velocity on the y-axis was originally 20 meters per second in the positive direction. But when it came back to my hand again, the velocity on the y-axis is the exact same magnitude, but in the opposite direction, negative 20. This is where we become asymmetrical. This is symmetrical motion, but after this point, when it falls down the building, this leg of the journey is asymmetrical. It doesn't equate to where we threw it. It keeps going. And so in 5 more seconds, it's here. And in 5.83 seconds, based on the height of the building, it reaches the bottom of the building. Or it hits the ground. And it hits the ground with a velocity of negative 37.1 meters per second. Wow. How do we figure that out? How do we do this? How do we figure out this motion? What equations can we use to figure this out? We can use the kinematic equations. And the kinematic equations are going to be using that one. You know, depending on what I'm looking for, if I care about the time, if I say, okay, how long does it take for the ball that I'm holding on top of a 50-meter tall building to fall down to the ground, right? If I'm at the top of the 50-meter tall building, where actually my hand is 50 meters above the ground. I think that's the better way of saying it. If we said if I was on the top of, if a man was, who is 2 meters tall, is on top of a 48-meter tall building, and his hand is, you know, at the height of his head, as an example, and he's throwing a ball up in the air at 20 meters per second, how long does it take for it to fall down to the ground again? Well, we could use our, if I say how long, I'm looking for time. I'm looking for time. So which equation would that be? Let's take a look at the kinematic equations again, when we loop back. Okay, so I want to look back at kinematic equations, and I want time. So this one is no good. This one seems to be the one that I can probably use, right? Because I have acceleration, I'm probably going to use this one, right? Probably. I can look and see if there's other ones I can use to make my life simpler, because I have this square here, t squared. T squared means there's always going to be more than one case. Maybe there's something simpler. How about this one? So I have my final position, and I have my initial position. Okay? So if my final position, I know my final position is negative 50, right? As an example. Because that's the height of the building. That's the height of my ball that I threw up. Okay? Can I use this somehow to figure out, how long it takes? Well, the problem is I don't this says nothing about acceleration. So therefore, this is something that I can't use. All right? How about this one? Can I use this one? It says nothing about time. I want time. And how about this one? Maybe. My final velocity at the bottom is going to be 0. My velocity initial, it says something about my initial velocity because my initial velocity is 20, right? And I also have this, acceleration that's up here. So my acceleration in terms of G's is negative 9.8. And I want to find time. So I know if my initial velocity is 20, let's try and use the calculator for this. Let's sub in some numbers here, right? So I'm going to just bring up my calculator. Let's see if this works. I mean, again, I'm trying to simplify, right? To show you which one we can use. So if I say my initial velocity is 20, right? And plus negative 9.8 times time, I want to find time. So let's sub in the values is what I'm saying, right? So let's write this equation. So I want to insert a text box. By the way, for you guys, if I give you something to write, like an equation on your assignment, I recommend inserting, as an example, the equation right here. You can do that with both PowerPoint and Word. Okay, here's my equation. And I can start typing here. So I can say that what I'm looking for is, let's try that again. Wow, I'm suffering today. So I say if the final velocity, right, if my final velocity ends up being 0, right, because my final velocity, and that equals to my initial velocity, which is 20, right, plus I have a negative 9.8, right, which is what I have there, times time, and I want to look for time. Does this give me the numbers that I need, right? So let's solve for t then, okay, because that's what I want to do. When I do an equation, I want to rearrange this stuff so that t is on one side and everything else is on the other side, all right? Again, I'm just trying to see if this works. Who cares about anything else? Just these two things, all right? So I move the 20 over on the other side. This becomes negative 20, right? And this becomes 0. Okay, so then it's negative 20 on the left side. Then I take this as an example, this negative 9.8, and move it to the other side. I divide both sides by negative 9.8. Both sides divide by negative 9.8. So that means the next equation is going to look like this. So instead of this, let's insert a equation, and I want to use y over x, fractions, that you can put in here. So I want to say that this is 20, right? And this is negative 9.8. Negative over a negative is a positive, so we lose the negative symbol over here. Okay, so then we have what remains then is this equation. T is equal to 20 over negative or over 9.8. Let's see what that works out to be. So 20 divided by 9.8 then, we figure it out as 2.04. Okay? So we're going to say that that's 2.04. And by the way, typically I'll ask you for a number of decimal places. 2.04, if I said 3 decimal places, it's going to round the 8 to a, it's going to round the 0 up 1 to a 1. 2.041. So what we're saying is when the velocity is 0, right, it takes 2.041 seconds for the velocity to be 0. But my friends, this is only half of the picture. Why? If I go to the tower that we looked at, which is this tower, what this means is how long does it take for me to slow down to get to be 0? And like it says here, there's your 2.04. It takes 2.04 seconds to come here. 2.04 seconds to come here. Uh-oh. Now we've mapped this. From here to here, we can map by taking this 2.04 and multiplying it by 2. 4.08 seconds so far to come to here. Okay, now, but what about if I want to match from here downwards? Well, that's a different equation. I can start off with a velocity here because it's falling. I'm not throwing it. I'm throwing it. It's a velocity that starts off at -20 with in the same direction, right? How long does it take for me to go from here, right, in at this height to the bottom? And I want to travel 50 meters. How long does it take me to go 50 meters, right, when I have a velocity of -20 and an acceleration of -9.8? How long does it take me to go 50 meters? Okay, that means I need to equate distance or displacement with time. Is there something that gives me displacement in time? So I go back to my kinematic equations. This one does not give me displacement in time. All right, I want to find the total time. This one does give me displacement in time, but I want to avoid it, right? Because of this square. This square, t squared, it gives me potentially two different answers. Okay. How about this one? Does this one give me an equation of time and displacement? And the answer is yes, but I'm missing acceleration. Okay. Displacement in time, my friends. You can see that there's no displacement in time here. So I'm stuck with using this other equation, right? Because this does not tell me about displacement in time. This tells me about velocity and we can, by the way, use more than one of these to figure this out. But this is the one that I would use. Okay, so now I can plug in some values here. So let's do this one. Again, I'm working with a -20 velocity. The initial position is positive 50. All right, so positive 50 is the initial position. So let's write the stuff in that we know. So again, I'm going to go down in here, and I'm going to put in a formula. I'm going to insert our equation. There's our equation. And I'm going to start writing stuff down. So I'm going to say that, okay, we know that the final position is, and again, there's different ways to see this, is 0. That's the final position. Okay? If the final position is 0, then the initial position must be some positive amount. For example, 50. Okay? If the final position, if that's the way we're taking it. However, we can also look at it as if the initial position is 0, right? That means from our hand. If we can also see it the other way around. Okay, is what I'm saying. And our final position is a negative value, right? That's also a way to see it. So now we have to see which one works the best. Okay? So I can say that 50 is the initial position plus v initial times time, right? Our initial value is 20, but on the negative axis, 20 times time. We don't know what time is, so we're going to leave the t in there. This is where it becomes hairy for us. Plus, we want to do 1/2 of at squared. We know 1/2 of a, which is 9.8 divided by 2, right? So it's 9.8 divided by 2. It works out to be 4.9, right? Times time squared. Okay? Time squared. Does that make sense? That's the equation. Guess what that is, guys? It's a quadratic. In order for us to serve or solve this equation, we need to use the quadratic equation to solve it, right? Which means the total time is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. What equation am I talking about? I'm talking about the quadratic equation. Quadratic formula. This one. Okay, let me just take a snapshot of that and I'll bring it in. Okay, so you can see it. This becomes, that didn't work. Let's take a snapshot of this, I said. This one. All I care about is this. All right? And bring it in. right? So if we have this is the formula that we would need then, right, to figure this out. We want to find time, that's what x is in this equation, right? And we want to sub in values for b. By the way, this is a, right? Actually, it's nicely named. B is velocity, and c is position. Okay, that's what we do. So we'd sub in values in here. So if you were going to do this, let's do it. We would start off with a different equation. We would start off with this equation. So let's do minus b, right? We'll say plus or minus. Let's do the plus first. So plus the square root of the square root, and I think it's I think I can put a square root symbol in here. Insert square root symbol. There we go. B squared. So what is b? B is 20. Minus 20. Minus 20 times minus 20 is 400. The negative sign gets canceled out, right? Because that's b. This is c. This is a. Okay? Minus 4ac. So minus 4ac. 4 times. This is all under the square root, guys. Sorry, it doesn't show properly. A, which is 4.9. By the way, this is a negative. One thing we don't want to do is we don't want to show this incorrectly. It's a negative 4.9 because it's gravity, right, in that same direction, right? Negative 4.9 times c, which is 50. Okay, so that is all under the equation. Let's see when we simplify, and this is all over 2a, right? So this is all over. We're going to say that that whole thing, this part, I'm just going to put this all in brackets here, which is not showing properly for the square root. It's all over 2 times a, which is acceleration. Our a is 4.9, so now it becomes 9.8, negative 9.8. That is the equation here that we have to figure out, all right? So now that we do this, and minus b, of course, is negative 20, which is positive 20. Right? And that's what t is going to equal to in a second. And I don't want to take too much time with this, but we want to go through this exercise once. Okay, just once. I'm not going to try and go through this exercise too many times. Okay, let's simplify under the square root. So again, it's 400 minus, so minus times a minus is a positive, thank God. So it's minus 4 times 4.9, right? Which works out to be whatever, times 50, right? And then plus 400. So that works out to 1380 under the square root. So we want to find the square root of that, which is 37.14, all right? And we want to divide that by a negative 9.8, right? So divided by 9.8 negative. So where's that plus minus? So negative 3.791, right? So that's the first option. Negative 3.791. 20 minus 3.791. Does that make sense? Right? 20 plus a negative 3.791. So if I said 20 plus that negative value, right, as an example, then that would be 20 minus 3.791. So we think that it's going to take 16 seconds for it to go in this particular case. I probably made a mistake somewhere, for sure, because it should be much smaller than that. Okay, but that's the idea. Yeah. Sorry, isn't the acceleration negative 2? You missed the 2a. 2a. You know what? I did, but I said 2 times a is negative 9.8. Right? That's what I said here. So hopefully you got that. 2a, a squared. Yeah, I think so. I think I got everything. I just miscalculated something for sure. But the idea is the same. So we get this idea where we simplify for this thing, and it ends up being 16.29, which is actually the wrong number. But the idea is, what we're doing is correct. The idea that we're doing here, b is negative 20, and we're saying it's a negative b, right? So negative 20, which is positive. Okay? So that's how it works. That's how the equation works. So if we're going to do if we just put a negative sign there, right? So instead of a positive, I would put a negative, and because the outcome is negative, we would actually add 3.71, which wouldn't make any sense. So that's why it's got to be negative. It's got to be a positive, all right? It's just that what we did under here was wrong, right? So let me just look at this one more time to see if I'm right. So 20 times 20, right? It's 400, right? 400 minus 4a, a being negative 9.8. Oh, there we go. Yep. But that's a. No, a is this, not negative 9.8, because we've divided by 2. So what a is, this is right. So negative 4.9 times 4, 4ac over 2a. ac minus 50. What did we do wrong? There's something that we did wrong here. Just give me a sec. Maybe you guys can see it, and I can't, but it's okay. So let's try this again. So 4 times 4.9 might be some kind of really stupid calculation. 4.9 times 50 plus 400. No, that looks right, which is 1380, right? And then that is square root, which is 37, and then divided by 9.8. Yeah, 3.79. The numbers look right. My execution is probably wrong. All right, but this 20 is wrong. But that's normally what you do. You take your values and you put them, you kind of divide them, and you have to use the quadratic equation for you to get this, where ax squared plus bx plus c is equal to 0, which is what this is. ax squared is this, where t is x. Here it's a negative sign, right? As an example, minus 20 was b. B is equal to minus 20, and 50 is the height. All right, so that's how we figured out, that's how you would, that the kind of way, although we calculated it wrong, that you would figure out this. You'd figure out the distance between here and here being 50, and then you ended up, the time should be 5.83, not that other value that I have. But that's how you would figure it out. You use the quadratic equation for that. Wolfram Alpha. Thank you for that, Wolfram Alpha. Check your 0. Yeah. Okay, so that is how that works. And we can also look at the kinematic equations from calculus. I'm just going to keep an eye on the time here, so I don't want to rush overtime. Where the displacement equals the area under the velocity of the curve, time curve. Area under the curve is integration. The limit of the sum is a definite integral. In other words, what we want to try and do to find the area of under the curve is we want to take little time slices. We want to take little rectangles and add all the rectangles up as close as we can to estimate the area under the curve. And this is how the old philosophers used to do it. And then they would integrate by adding all these little rectangles up, because it's easy for us to calculate length times width, but very difficult for us to calculate the area under the curve without calculus. So using the area under curve is the change, the rate of change from of time, so time final minus time initial of the integral of the velocity. The integral of the velocity is the antiderivative of velocity, which means I want to go the other way back. I want to get that position time graph from the velocity. I want to do the antiderivative. And once I do the antiderivative, I do the antiderivative for time final minus the antiderivative from time initial, and then I get the area under the curve. Nicely. All right. So we have these kinematic equations that we get from calculus. And I'm just going to show them to you one time, and we're going to move on. Okay. So the integration form of v final minus v initial after you do a proof gives you that v final minus v initial is equal to at. And then when you work the magic on this and rearrange stuff, it basically you can actually come up with the same equations. That's what they are. They're proofs that the same equations work for the ones that we just used. So again, general problem solving strategy. We conceptualize We categorize, we analyze, and then we finalize. Those are the 2 things we do, or the 4 things we do. So when we conceptualize, we want to think about and understand the situation. Usually we make a quick drawing, and actually one thing that people in Japan do differently than the people here in the West is they do a lot of drawings. They try and draw the situation as much as possible to try and understand it, to visualize it in their head, right? And so you can actually physically see it, like in a drawing. And then once you conceptualize it, you start to simplify the problem by classifying what type of problem it is, right? And then what you do is you start analyzing the problem and add units, apply your equations to see if you know how to figure out that problem. Then you check the result and you finalize to see that you kind of sub back into the original equations with the original problems to find the answers. Okay, so here's some problem solving. Final ideas is you want to break a big problem into subproblems. We kind of did that, although we did the second part wrongly, with our the example of the person on the top of a hill. We did that, but we did it wrong. The last part, the asymmetrical part, we didn't take it's like a stone being thrown down as an example, as opposed to a stone being thrown up and then come down. All right, it's just like that part. We can break it into 2 parts. Right? So here are some practice examples, some practice problems for you. And this will help you with, don't have to use a domain when you use limit. Yeah, the domain is the y-axis. All right, so let's take a look at this, or the x-axis. A racing car starts from rest at t equals 0, all right, time is equal to 0, and reaches a final speed at v, whatever that speed is, at time t. If the acceleration of the car is constant during this time, which of the following statements is true? The car travels at a distance of vt. Is that true or false? What do you think, guys? If the acceleration of the car is constant during this time, right? Which of the following statements are true? The car travels at a distance of vt. Is that true or false? Okay, someone says true. The acceleration is not 0. The acceleration of the car is constant. So it can't be vt, because we have to add acceleration in there. So this is false. The average speed of the car is v over 2. The velocity over 2. Right? Is that true or false? Okay. Well, we can't do this because we know that the velocity is changing. Right? So the average of can't be v over 2. Because v is the speed, the final speed. We can't just use the final speed. We have to use both the final speed and the initial speed to find our average. This is wrong. The magnitude of the acceleration of the car is vt. And someone says all false. And the answer is true. And the velocity of the car remains constant. No, it does not, because it has acceleration. We know it's under constant acceleration. And so then the answer is none of the statements are true. Okay. Here's another one. Problem example. Next one. Actually, this is telling you that this is solving the things. It says only statements B and C are true. Statement E is not true because of these statements. So we were wrong. Problem example number 2. The position versus time for a certain particle moving along the x-axis is shown in the figure here. All right. So find the average velocity in the time intervals 0 to 2 seconds. Okay, so what is the average velocity from 0 to 2 seconds? Well, we know the displacement is positive. That's good. So it moves from time 1 to time 2. If we measure the units, 2, 4, 6, 8, 10 units. So it's moved 10 units over 2 seconds. 10 units over 2 seconds. So x final minus x initial over time. X final is 10 minus x initial is 0 over time 2 is 5. Would that not be the case? The next one is where b is from 0 to 4 seconds. Okay, so 0 to 4 seconds. That's a different story. Now we have, x final is 5, x initial is 0, total time is 4, 5 over 4. Okay, so a different kind of overall velocity. You can do the rest. And here's some problem examples that we give some answers to. I want you to guys to kind of look at this. I've left these here for you so you can see, you know, some of this stuff, because at the end of the day, we're going to have some of these things potentially prop up for you. And in lab, ask Spencer about some of this stuff if you don't understand. Here's one. A person walks. Wow, my PowerPoint seems to be skewed when I converted them for some reason. Really weird too. Terrible. A person walks at a constant speed of 5 meters per second along a straight line from point A to B. Okay? And then back along the line from B to A at a constant speed of 3 meters per second. What is her average speed over the entire trip? So think about that. Again, same kind of ideas. Speed is positive whenever motion occurs, so the average speed must be positive. For the velocity, we take as positive for motion to the right and negative motion to the left. So its average value can be positive, negative, or zero. The average speed during any time interval is equal to the total distance traveled divided by the total time, and this is the solution to problem 3. And it talks about it in more detail. Here's the last one. A particle moves according to the equation x is equal to 10t squared, right? Where x is in meters and t is in seconds. Find the average velocity for the time interval from 2 seconds to 3 seconds. How do you do that? Okay. So these are equations for you. Take a look at them. This is my my second or third last slide, and it gives you the some other problems. Other example problems. Find the instantaneous velocity of the particle described in figure P2.1 at the following times. T is equal to 1. What's the instantaneous velocity? Right? So if T is equal to 1, you know, as an example, what's the instantaneous velocity? Okay? Where I have my displacement is 4 x final over x initial, right? What's my instantaneous velocity here in 1 second? And finally, draw motion diagrams, so little arrows, as an example, of an object moving to the right at a constant speed, an object moving to the right at a speed, speeding up at a constant rate, so some kind of acceleration, and an object moving to the right slowing down at a constant rate. So similar to what we did above. So some examples of some practice ideas. But the one you want to solve is the one that we did wrong. How do I solve this problem, right? Which is, it's asymmetrical from this point on. So from here, from initial velocity at A upwards, and we can look and see what it says here. At B, the velocity is 0. At C, the velocity is negative, downwards. And the displacement, and look at this, the displacement is minus 50 meters, right? That ends up 50 meters below the starting point. So that's another way of looking at it. Remember I said that there's 2 ways of looking at this. You can look at this as if the starting point is down here, or if the starting point is up here. That would significantly change the arrangement of our equation, right? Because maybe minus 50 is C, minus 4AC over 2A, right? Which means that the numbers would be different than what we have right now, and that's what would cause our error, our miscalculation, okay? So that's a different way of looking at it, and that's probably where our error lies, okay? And we can simply see that if we actually go to that page that we were using that calculation, so in the Kinematic Equations area, which is here, right? If we reverse these numbers, if we said that this is negative 50, right, as an example, and that would be a positive 4.9, would it make a change? The negative 50, if we swap these things around, right? You might see a difference, but I'm not sure. I think there's still something else we're missing here. And I'm sorry, my brain is just not functioning right now, so I'm not thinking properly to figure it out. 20 divided by 1. Okay, any questions around the stuff we talked about in terms of, today we discussed motion in one direction, Okay, again, look for tonight. I'm going to have an assignment that comes out. It's mostly going to be a programming assignment that's going to be done in pairs, 2 people, right? One thing I asked you guys to do last week, if we go to Blackboard here, I'm just going to go over to Blackboard one sec. One thing I asked you guys to do, and let's see if actually it works finally now. Hey, now it finally works after I don't need it. If you go to Blackboard, we want to make groups, right? So users and groups, right? I want to create a bunch of groups for you guys. Now, we have a number of people in our sections, right? And if everyone has one partner assumption, right? And right now we have 72 participants. Let's say 80 people in the course. Let's just say I'm going to make 40 groups. So you guys can auto sign up for your groups, please. So it's going to be self-enroll. And I'm going to call this assignment groups. Okay. This is where the group idea came from. I don't care about any of this stuff. No blogs or discussion boards, emails, journals, tasks. Nope. None of that stuff. I just want to have groups where you can hand stuff in together, right? Group is visible to students, yes. And what I want is a sign-up sheet that says assignment groups sign up. I want to show the members, right, as an example. And did I do something wrong? I think I want you guys to auto sign up. Number of groups. Create a smart view for the group set, but maximum members. Maximum members is, we'll say, I'm going to say 3, okay? But I want you to move in, pick a partner first. And worst case scenario, if you can't find a partner or if you don't know somebody, I may stick you on a group. But for now, I will not, please do not sign up in groups of 3, sign up in groups of 2. Worst case, if I don't change this number, then what's going to happen is it'll prevent me from adding someone on to help you out. So number of groups is going to be 40. Okay, and I'm going to submit it. It's going to create those groups for you. So there's 40 groups. Please pick an assignment group. If you don't pick an assignment group, your assignment will not be visible to you, okay, for tonight. No, you cannot work alone. You have to work with somebody, at least one person. Okay? Pair programming. So please sign up when you have a chance. Again, this assignment is going to be due 2 weeks from now. All right, so it's not going to be due anytime soon. So it's not going to be like, notice the assignment's due like week 4, and it'll be at the end of the week when it's due. And I'm going to give you the assignment later on. No trio. Trio is not pair programming like Marara says. Mary. Okay, that's it for me today, guys. Thank you so much for attending. Where are these groups? Okay, where you can find them is under Blackboard, under, I believe, for me it's under users and groups. For you it's under, let's see if I can look at it as a student. So if I was going to look at it, I would look at tools, and then I would look at groups if I was a student. It's probably a groups area I probably missed.
It's at the top.
Yeah, here it is. So this is where I would look at it. And I would see the view sign-up sheet to join a group. And then you would see this sign-up sheet like this. And then you'd sign up for one of these groups. And you see there's no members here. Well, there's one member here. Group 11, Ian's already jumped the gun. And then someone's in there already. Okay? Please, here's what I'm going to ask you to do. Please do not, whatever you do not randomly sign up for a group where you don't know the person. If you randomly sign up for a group, I will remove you. First, try and discuss it with the other person, okay? That's what I'd like you to do first. So this way, what will end up happening is, the person has a fair shake to say yay or nay, okay? If you can't find a partner, I will help you find a partner. I will pair you up, right? So if you've joined a group, don't just join a group randomly. First, talk to your peers, your people that you know, and see if you can find a partner ahead of time, ahead of signing up. There's no rush. You get 2 weeks to submit, okay? So please do that today.
Sorry to interrupt, but did you say that we can be in threes?
Worst case, which means
Worst
if you can't
case.
find if one person it's uneven and they can't find a partner, then I will adjust it. I will make it so that you can work with somebody, a group of two. All right. I'm just going to end the video right now. Then we'll talk about administration.